This video module in the output analysis series is entitled Comparing Alternatives 1. And in this module, we will look at an example where we want to compare alternative configurations of a system. The system that we're going to use is from the law textbook. It's the zippy tell versus clunky tell problem, and you can see that we are comparing what we have labeled here as zippy on the left with clunky on the right. And this is an automated teller machine problem where the company has the alternative to buy either one fast ATM, which we'll call zippy, or two slow ATMs, which we'll call clunky. And in either case, we are going to assume that customers arrive at the rate of 60 per hour. The fast ATM, the zippy ATM, has a processing rate or service rate of 66.67, and the clunky or slow ATM has a processing rate, each one has a processing rate of 33.33. So you can see that we have the exact same processing rate. For zippy, it's just done with one server. With clunky, it's done with two servers. In order to make a comparison between these two systems, we need an objective. And so the objective for the comparison is the average time in queue for the first 100 customers, which they refer to in the textbook as D100. And so this is the metric that we'd like to use to compare the two systems. Before we look at the simulation, it makes sense to look at the steady state analysis. That's easy to do. So clearly this is an MM1 versus MM2 analysis. And so I just pulled out the with the utilization 0.9, and so I solve for the queuing metrics of interest. And if we're interested in time in queue, then at steady state at least, these are the two values that we have. So if our interest had been which system performs better or has a lower queue time at steady state, then there would be no need for simulation because the MM1 versus MM2 analysis gives us the exact values, and so we wouldn't need to simulate to find those. However, D100 is not a steady state value, and so it's certainly going to be impacted by the transient effect. Again, the first customer that arrives is going to find the system empty and idle. The second customer that arrives is going to find at most one person in line, and so on. So you have a transient effect at the beginning. And we probably wouldn't get to steady state with only 100 customers, even if we chose to ignore that transient effect. So clearly what we have if in this analysis is a terminating model or a terminating system. And so our goal in the video module is to use our Simio model of the system to make the comparison. So let's have a look at the Simio model. Let me pull up Simio here. Here's the model that we have. You can see it's a pretty straightforward model. We have a source object, a server object, and a sink object. And if we look at the source object, you can see that we use the maximum arrivals property under the stopping condition to say we want to have 100 entities arrive. And if you couple that with having an infinite run length or an unspecified end time, then Simio will, the source object will create entities until it gets the 100th one, and then it will stop. And then when there are no more events on the future event list, so in other words, after that 100th entity departs the system, the run will stop, and we will be able to measure the average time in queue over that time period. The second thing of interest, if we differentiate between our two configurations, let's go, see if I can get back here. We have what differentiates the zippy from the clunky is two things. The capacity of the server, so we have capacity 1 for zippy and capacity 2 for clunky, and the processing time. So zippy processes twice as fast. And so we implemented that using two reference properties. Go to the server object, and we have a num reference property representing the capacity and service time representing the processing time. And so if we look at our properties, you can see that we have the two properties here. And so if when we have num set to 1 and service time set to random exponential 0.9, we are simulating the zippy tell. So you can see that we have a single entity being served at any one time. Whereas if we stop the model and change to 2 and then change the processing time to 1.8, so half as fast, you can see that we now have simulated clunky tell. And so the objective here was to develop a single model that we could use to do a side-by-side comparison of our two systems. When we go to our experiment, we see, as usual, that we have our two reference properties set up as experiment controls. So we have num and service time, and we have two scenarios that we've defined, one called zippy, where we set the number to 1 and the processing time to mean to 0.9, and one called clunky, where we have two servers and the processing time mean set to 1.8. We've defined one experimental response because we're only interested in the average time in queue. So let me see if I can stretch this out here, and we see that the expression is server1.inputBuffer.contents.average time waiting. And so since we've limited the run to 100 entities long, then this value in the response will be our objective. And so let's run the model. I have 25 replications set for each. You can see, it's a very simple model, so it runs quite quickly. So if we look at our time in queue metric, our objective is to determine which one has the smaller time in queue. Again, nobody likes waiting in line, so we're interested in finding the configuration, in this case zippy or clunky, that has the smaller expected time in queue. And so the question at this point is, we have two observations here based on 25 replications of each run. The average time in queue in minutes for zippy is 4.867. while as for clunky, it's 3.9131. And so the question is, can we stop now and declare that clunky is the better configuration based on the response values? And so hopefully you realize that the answer was no, we cannot, because as we know, these two values represent averages of 25 samples. So we have a sample size of 25 from an infinite population. And we know that this type of estimation, estimating the average time, is subject to sampling error. And so we usually measure sampling error using a confidence interval. So if we look at our response results, you can see the zippy SMOR plot and the clunky SMOR plot. And what immediately jumps out, at least immediately jumps out at me, hopefully to you also, is the width of the confidence interval about the mean, the big beige area. And as we know, this is the confidence region for our estimate of the mean. And you can see that we have quite a big confidence interval here. And in fact, when we look at these values, while the mean that we have for clunky is indeed smaller than the mean for zippy, it's certainly possible that the true mean might be somewhere up in this area, still within our confidence interval, while the true mean for zippy is somewhere down here at the lower end of the confidence interval. So in other words, we have no way of knowing within this region where the true mean is. Now, this comparison, this side-by-side comparison of the confidence intervals and the SMOR plots in this case, is just a visual representation. What we really need is a statistical representation. And so to do that, we are going to use the paired t-test to do a direct comparison. So hopefully you've all seen the paired t-test in your statistics course, but let's review exactly what we're doing. We are letting A be the metric that we saw for the first 100 customers for ZippyTel. So this is the first replication average, the second replication average, third replication average, and so on. Similarly, let B be the replication averages for ClunkyTel. So first replication, second replication, and so on. So we're going to define the new random variable Z by subtracting A minus B for each replication. And then the paired t-test basically computes a confidence interval on Zn. And the null hypothesis for our hypothesis test is that the two means are equal, so we're collecting evidence to say that they're different. And the evaluation is, if the confidence interval contains 0, do not reject H0. In other words, when we compute the confidence interval, if the confidence interval contains 0, then we don't have enough evidence to declare that the means are not equal. So let's see how we can do this with our Simio model. So I'm going to go back to our run, and what we're going to do is we're going to export the details from our SMOR plot. And what will happen is it will export to the CSV file. Oops, don't show this again. I don't want to see that. And you can see that the way Simio exports is that I have my scenarios just stacked on top of each other. So here's my 25 clunky replications followed by my 25 zippy replications. So I'm going to just grab all these guys and reformat this just a little, reformat it a little bit, make it a little bit easier to see what's going on. So let's cut those out and let's paste them in right here beside it. And so now we have rows representing the individual replication. And so this would be the B random variable from our previous slide, and this would be the A random variable. So what we want to do is compute Z is equal to A minus B. And so I'll simply take the value of each individual replication zippy, subtract each replication value of clunky, and do that for all 25 replications. And so this column H represents our new random variable Z on which we want to compute the confidence interval. So let's do that. We'll just grab the average here. Average H2 to H26. Then we'll get the standard deviation. Standard deviation H2 to H26. Then we need the t-statistic, and so we're going to use t-inverse, and we want to do an alpha level of 0.05. And so we have 25 replications, so that would be 24 degrees of freedom. And our t-value is 2.06, and so on. So we can compute the half-width of the confidence interval. The half-width of the confidence interval is equal to t times the standard deviation divided by the square root of n, the number of replications. And so the half-width of the confidence interval is 0.03811. Also note that we can use the confidence function. We want to use a t-confidence interval. So we can put 0.05, then our standard deviation, and then the size. So we have 25 replications, and you can see that the confidence function gives us the exact same half-width that we computed manually. And so that we can compute the confidence interval, there's the lower and the upper of the confidence interval. I simply take the average minus the half-width to get the lower value, and the average plus the half-width to get the upper value. And so you can see here that we have minus 0.022 to 0.053. And so, in fact, the confidence interval that we computed does include 0. And because of that, we would say that we don't have enough evidence to reject the null hypothesis. In other words, we can't say that that the clunky tell is statistically better than zippy tell based on the evidence that we. So back to the original question, back to our Simio model, when we look at these two values, and the answer to the question of which configuration is better is that we don't know. While the mean value, it looks like the clunky tell is better. When we incorporate sampling error using our paired t-test, we don't have enough evidence to make that declaration. So let's have a quick look at what's going on here with this with the paired t-test. I want to make sure that everyone understands how we're computing this and what we're actually doing. So what I'm going to do is I'm going to use an alternative formulation of the paired t-test. Perhaps you've seen this, which is we compute a test statistic based on z bar n divided by the standard error, n over square root of n. And so if we do that on Excel, let's just do that so I don't have to do this by hand. This is t0, and so this is z bar n, which is the average, divided by the standard deviation divided by the square root of n, which is 25. And so we get a t0 value of 0.866 approximately for our test statistic value. And so if we go back to here, we can see that if we look at the t distribution, this is what we have. So this is, let's say this is our t distribution within degrees of freedom. And so the critical value right, that we computed when we looked up the t statistic. Let's go back here, and we looked up this critical value at the 0.05 confidence level, let's just do it at 2 decimal places, so 2.06. What we see is that what we have is 2.06 and negative 2.06, centered at 0, of course. This area is equal to alpha over 2, because we're doing a two-tailed test. So in our case, if alpha equals 0.05, then this equals 0.025. And so that's the meaning of that level of significance value. And of course, our value that we computed, what was it, 0.89 or something like that? Let's go back and take a quick look. The value that we computed for our test statistic is 0.87. And so we have a value here this is our t0 of 0.87 that we computed from our value. And so that you can see that what we have is, if the test statistic value is between the 2.06 and negative 2.06, then we would fail to reject the null hypothesis. So that's this alternative formulation of the paired t-test. And what's going on is that this level of significance value we split between the right side and the left side. One quick note about when we're looking up these t-values, you might notice that when we did the t-inverse function in Excel, we use the 0.05 value. And the reason we do that is because Excel, the function t-inverse, automatically returns the two-tail inverse, right? So we didn't have to cut that value in half. However, if you're looking this up in a table, let me see if I can grab the table that we use. You might have to, depending on the structure of the table. So in our table here, you can see the graphical view gives us our T alpha and then specifies alpha as not the two-tail, but the one side. So in this case, we're going to use alpha over 2. And so if we go to our 24, there's our 24 degrees of freedom. Alpha over 2 is 0.025, and there you can see the 2.06, which is the same value that we got in Excel. So the critical part here is to pay attention to either the function that the software gives you or the table that you're looking up to make sure that you understand exactly which t-value you need to use. So at this point, now that we've shown that we don't have enough evidence to declare that clunky is better, we basically have two choices. We can either be satisfied in saying that there's no statistical difference between our two configurations, or we can choose to run more replications. And so if we run more replications, of course we know that's going to tighten the confidence intervals. And if we just jump to 100 replications, again, it runs pretty quickly. Just take a quick glance at our responses, and you can see, in fact, our confidence intervals have tightened up quite a bit. If we check this using the paired t-test, the same method that we did before, we could export the details and so on, but I've already done that, so we don't have to go through that. So look at the comparison. Again, the exact same process that I followed before, except this time I have 100 replications. And if we scroll down, we can see that the lower value of the confidence interval is 0.00098, and the upper is 0.0305, and so 0 is not in the confidence interval in this case. And so we also see our t-naught value of 2.10 and our t cutoff value of 1.98. And so our test statistic is in fact larger than our cutoff value. And so if we look at that in terms of our t distribution, we had this this value was, I can't remember what the values were. Let's jump back here. This was 1.98 and 2.11. So this is 1.98 and then 2.11. So we are in fact larger, and so we would reject the null hypothesis in this case and say that the means are not equal, and because the clunky-tel has a lower value, we would say that it's the preferred configuration. And so you can see that if we do our initial run and we don't have a statistically significant difference, we can choose to run additional replications, or we can just stop and say there's no difference. And so this process would be you would continue to run until you decide that there's no statistical difference or not a discernible difference that's important to you. So the focus of this video module was on comparing alternatives, and in particular how we can use the paired t-test to incorporate sampling error into our decision. But before we go, I wanted to give a quick pointer on the subset selection tool that Simio provides that provides very similar functionality. So in this case, we've already run our 100 replications and we've done the paired t-test, so we already know that there's a statistical difference. Oops, someone adding stuff to my Dropbox. But we can also see this if we go to, if we select the response and then do subset selection, and then you can see that we have two different colors of responses. And so the module's not going to discuss the details of subset selection. That's in another module. But let me just say that what it does is separates the scenarios into two groups, the non-optimal group and the potentially optimal group. And since we have only two scenarios and the subset selection has done the separation, we can say that the zippy is not in the group, so this is in the non-optimal group, and the clunky is in the potentially optimal group. But since it's the only one there, then in this case, it's the better of the two. Also note if we go back to our original 25 replications here, let's just rerun that. And then we'll do the same thing. So we'll go to TIQ, do subset selection, and then on highlight, you can see that there are not two colors. So the subset selection was unable to partition our scenario. So again, exactly the same results that we got with the paired t-test that says we don't have enough separation between the two. We don't have enough evidence to say statistically that one is preferred over the other.